This video will cover Section 3, Antiderivative of Formulas. The objective of this video is to review the antiderivative rules, which are the building blocks of integration. Let's start by recalling the derivative rules, or our building blocks for derivatives. Antidifferentiation is going backwards through the derivative process. So the easiest antiderivative rules are simply backwards version of the easiest derivative rules. Recall from chapter 2 that the constant multiple rule for derivatives was that you take the derivative and pull out the constant. For sum or difference, when you take the derivative of a sum and difference of differentiable functions, you can take the derivative over the sum or difference. For the power rule, when you take the derivative of the power, you multiply by the original power and subtract 1 from the original power. Special cases of this are the derivative of all constants is 0 and the derivative of x is 1. For exponential functions, we have that the derivative of the natural number e to the x is e to the x, and the derivative of any other base is a to the x times natural log of the base. And then the derivative of the natural log, ln of x, is 1 over x. Let's see all of these in reverse. In what follows, we'll assume that f and g are differentiable functions of x, and k, n, and c are all constants. So in each of these cases, we're looking at the indefinite integral when we're talking about antidifferentiation rules. You should note that a definite integral will always have a numerical answer. An indefinite integral will result in a family of functions, so don't forget the plus c. So looking at the constant multiple, when I'm integrating a constant multiple of a function, I can pull the constant multiple outside of the integral, just like I could with derivatives. When I'm taking the integral of a sum of difference or functions, I can integrate over that sum and difference. So if I look at the integral of f of x plus or minus g of x dx, I could instead take the integral of the first function plus or minus the integral of the second function. Now for the power rule, we want to do the reverse of the derivative power rule. So the integral of x to the n dx is going to be adding 1 to the original power and dividing by that new power plus c. As long as n is not equal to -1, that would make the denominator equal to 0. In the case where we're integrating just a constant, it is k times x plus c, since k is k times x to the 0. For exponential functions, since the derivative of e to the x is e to the x, then the reverse is the same. So the integral of e to the x is e to the x plus c, family of functions. And the integral of a to the x dx is a to the x divided by the natural log of a plus c. And finally, the natural log, or the integral of x to the -1 is equivalent to the integral of 1 over x, which is the natural log of the absolute value of x, because we want to make sure whatever we plug in for x is a positive number, because we cannot take the natural log of a negative number. And then don't forget that plus c, because we're looking at indefinite integrals, and so the antiderivatives are a family of functions. Let's take a look at a couple examples. We'll start with indefinite integrals, and then we'll look at definite integrals. For part A, we're looking at the indefinite integral of the square root of x plus e to the x minus 1 over 4x cubed dx. We'll start by arranging the integrand, which is the piece inside of the integral and the dx, thinking of our integral and dx as a parentheses as we described in the previous video. We'll rearrange this so that we can apply one of the rules that we discussed in the previous slide. So we're looking at the integral of x to the 1/2. So when you have a radical, the denominator of your fractional exponent is the root, and the exponent on your variable or radicand is going to be the numerator. Plus e to the x minus 1/4 x to the -3 dx. The only reason the x to the third moves to the numerator with the negative power is because the 4 is not raised to that power, so we want to leave it where it is. Now we can apply our different anti-differentiation rules. So the first and third term of this sum are going to use the power rule, and then we'll also be using the sum and difference rule over the integrand. And then we'll also be using the anti-differentiation rule of exponential functions when it's base e. So I have x to the 1/2 plus 1, and then we're dividing by the new power 1/2 plus 1. So we're always adding 1 to the original power and dividing by that new power. plus e to the x minus 1/4 x to the negative 3 plus 1, and then divide by that new power of negative 3 plus 1. And then we have to add on our plus c because this has to be a family of functions for indefinite integrals. That's a really important key. You don't want to forget that plus c. The work from here is going to be simplifying this to get it as close to the original form of the integrand. So I'll have x to the 3/2 divided by 3/2 plus e to the x minus 1/4 times x to the negative 2 divided by negative 2 plus c, 2/3 x to the 3/2 plus e to the x plus 1/8. This comes from 1/4 times negative 1/2. That gives us the positive, and then x squared. I move that negative power down to the denominator to make it positive. And I could take one more step to rewrite x to the 3/2 as the square root of x cubed, put it back in radical form. And so we see that the antiderivative is 2/3 times the square root of x cubed plus e to the x plus 1/8x squared plus c. In part B, we'll approach this in the same way as part A. We'll rewrite the integrand to simplify it a little bit to apply the rules discussed on the previous slide. So let's start by rewriting the integrand in the following way. We'll have t to the 5th over t minus t squared over t, so we can simplify the fractions. So we're looking at the integral of t to the 4th minus t dt. We'll use the power rule and the difference rule for antiderivatives. What we have is t to the 4th plus 1 over 4 plus 1 minus t to the 1 plus 1 over 1 plus 1 plus c. We'll have a family of functions that represent the antiderivative of the integrand. We have t to the 5th over 5 minus t squared over 2 plus c. That's our indefinite integration, making sure to always add the plus c when there's no limits of integration. Let's look at using antiderivatives rules and the fundamental theorem of calculus together to evaluate definite integrals. So just as a reminder, we will have a numerical value as the result here. And so let's start by evaluating the antiderivative of the first term. We're looking at x to the 2 plus 1 divided by 2 plus 1 plus 4x to the 1 plus 1 divided by 1 plus 1 minus 3x plus c, that's the antiderivative, and then evaluated from 1 to 3. You might see this different notation, but I like to use a vertical bars. Some people use brackets. So we're looking at x cubed divided by 3 plus 4x squared divided by 2 minus 3x plus c, evaluated from 1 to 3. And then one more simplification step before we apply the fundamental theorem of calculus. And so the fundamental theorem of calculus says that we will evaluate f at 3 and minus f at 1. So we're looking at 3 cubed over 3 plus 2 times 3 squared minus 3 times 3 plus c minus 1 cubed over 3 plus 2 times 1 squared minus 3 times 1 plus c. Notice that we have a plus c minus a plus c, and then the c's do cancel here. They do go to 0, and that is why we don't end up with a plus c in our definite integrals. This will be the case every time we do a definite integral. And so we're looking at 27 over 3 plus 2 times 9 minus 9 minus 1 over 3 plus 2 minus 3. And so the definite integral from 1 to 3 of x squared plus 4x minus 3 dx is 56 over 3. In part B, we're looking at the integral from 1 to e of 1 over x dx. Remember from our antidifferentiation rules, the integral of 1 over x is the natural log of the absolute value of x plus c, and then we'll evaluate this from 1 to e. the natural log of the absolute value of e plus c minus the natural log of the absolute value of 1 plus c, using the fundamental theorem of calculus. Again, we have a plus c minus c. The natural log of e is the absolute value of e is the natural log of e, which ends up being 1, and the natural log of 1 is 0, and so our definite integral here is just 1. In the next video, we will discuss a technique to integrate whenever we have a derivative that came from the chain rule.